Good morning. This is my master's thesis defense. The title of my thesis is a model of the structure-function relationship of the pulmonary artery in recovery from hypoxic pulmonary hypertension. I'm going to start off talking about the outline of what I'm going to talk about today, and the first part is going to be the introduction and background. This includes pulmonary hypertension, explanation of strain energy functions, a summation of Sean Burgett's work, who many of you know, a doctoral student I work with, and then I will get into my hypothesis with my 3 aims, and each aim is going to be broken down into a methods and results section, and I'll conclude with limitations and future work. So first, the disease I'm studying is pulmonary hypertension, and this is a disease with a broad etiology. The formal definition of pulmonary hypertension is a pulmonary arterial blood pressure above 25 millimeters of mercury. If you look on the left here, this is a cartoon summing up the main attributes seen in pH. On the left, we have a pulmonary hypertensive heart and lung, and on the right, we have a normal healthy heart and lung. And so we can see in the pH heart, we can see that the right ventricle is enlarged. This is a phenomenon referred to as right ventricular hypertrophy. We also notice that the vessels are much thinner compared to the normal heart and lung, as well as the vascular dropout occurring in the lung and the peripheral vasculature. As I said, pulmonary hypertension has broad etiology, and so the World Health Organization has 5 major classifications. The first, and where most of the cases occur, is pulmonary arterial hypertension. The second is pulmonary hypertension due to left heart disease. The third, and the focus of my research, is pulmonary hypertension due to hypoxia and lung disease. The fourth is chronic thromboembolic pulmonary hypertension, and the fifth is pulmonary hypertension due to multifactorial mechanisms. I want to point out the main difference between class 1 and class 3 is that we know the cause for class 3, and that it is hypoxia, where class 1 contains many idiopathic cases. In order for us to understand the pulmonary artery in its mechanics and pulmonary hypertension, we have to first understand the arteriolar structure. It's composed of 3 main layers. The innermost layer is the tunica intima, the middle layer is the tunica media, the outermost layer is the tunica adventitia. This is a diagram of the pulmonary artery with a transverse cross-section from the wall. The innermost layer, the tunica intima, is composed of endothelial cells on a basement membrane of collagen. And its primary function is to serve in regulation of the vessels in response to changes in blood composition, such as protein composition, oxygen levels, and blood flow. It is separated from the medial layer by an internal elastic membrane, and the medial layer is composed of smooth muscle cells throughout a matrix of collagen and elastic fibers. And its primary function is to serve in actuating vascular tone through regulation of vasocontraction and vasodilation. The outermost layer, separated again from the media by an interelastic membrane, is the adventitia, and it's primarily composed of fibroblasts throughout a matrix of extracellular matrix proteins, and its primary function is to serve as structure for the artery. So my research is focused on the medial layer, and this is because it regulates vascular tone. We know this to be true because studies have shown that in response to hypoxia, endothelial cells will produce nitrous oxide and endothelin, which will then be recognized by the smooth muscle cell, cause a depolarization of the membrane through potassium ion channels, cause an influx of calcium, intracellular calcium, and subsequent actin-myosin contraction. And so this is important when understanding pulmonary hypertension. Chronic hypoxia induces pulmonary hypertension. If we look at this pulmonary artery on the left, we have normal, healthy pulmonary artery. And again, it's composed of the 3 main layers I mentioned, the adventitia, the medial layer, and the endothelial layer. And if we expose it to hypoxia, we get a myriad of reactions, most notably vascular remodeling in the form of thickening of the adventitia and medial layer, as well as production of certain species such as hypoxia-induced factor, reactive oxidative species, IL-6, which is an inflammatory marker, and NF-kappa beta. And this in turn causes a myriad of reactions such as fibroblast proliferation, as well as expression of myofibroblasts due to expression of smooth muscle actin, proliferation of smooth muscle cells, proliferation of pulmonary arterial endothelial cells, as well as increased presence of inflammatory markers such as macrophages and dendritic cells. It's important to note that this process is thought to be reversible and that hypoxic pulmonary hypertension is mild and can be thought to revert back to the healthy symptoms seen here. And so this vascular remodeling process that I mentioned results in increased vessel stiffness. We can see this from a purely geometrical standpoint that if we look at the normoxic pulmonary artery on the left here, defined by a certain thickness, we expose it to hypoxia and there's an increased thickness, we can characterize the wall stress. What do I mean by wall stress? Wall stress is any stress felt on the arterial wall in any direction. And its general formula is the pressure times the radius divided by its thickness. We can see that as thickness goes up, our wall stress goes down. What's not so intuitive is the concept of the elastic modulus, and this is an intrinsic material property that describes the deformation behavior of a certain material. And so if we take this material and we stretch it, and we define the wall stress over the stretch, the modulus is equivalent to the derivative of this wall stress over that stretch. And so when we talk about stiffness, the primary definition of stiffness is the change in volume over the change in force over the change in diameter. And so this is also proportional to the modulus with geometrical constraints in the cross-sectional area divided by the circumferential length. So we can see if modulus goes up, our stiffness will increase as well. And so we can begin to understand these mechanical properties, mechanical behavior with deformation mechanics. So if we take this pulmonary artery on the left here and we define it with a certain pressure and a certain diameter 1 with a cross-sectional area A, and we increase its pressure and it has a subsequent increase in diameter, we can take these pressure diameter points and plot them and be able to extract this information. It's important to note that the cross-sectional area here is equivalent to the cross-sectional area when you stretch it. That is referred to as isovolumetric deformation. So again, we can plot the pressure versus diameter, and we can get a series of points over a range of pressures, and this slope of this line is equivalent to the stiffness. It's important to note that this is in the extrinsic domain and that these parameters will change due to deformation. And so we can convert this into the intrinsic domain of stress versus strain and plot this line, and the slope of this line is equal to Young's modulus. As I said, this is material property. And so we can do this for our materials. And it's important to also mention residual stresses. So I mentioned wall stress. Residual stress is defined as the wall stress at a zero stress state, in which it defines the tensegrity of the vessel. And what I mean by tensegrity is tensional integrity. At zero stress state, it is the structure and stability of the material that will define how it behaves at higher pressures. And again, we can look at this from a geometrical standpoint in this artery on the left that is intact. And if we cut it along its longitudinal axis, we have an opening angle here. And this opening angle is proportional to the residual stress seen in the structure. For example, if we have a more narrow angle, we have higher residual stresses. If we have a wider angle, we have more lower residual stresses. And so again, this is important when understanding the way a material will behave at higher forces, which makes sense for studying diseases like pulmonary hypertension in which our pressures are elevated. And so we can characterize the stress-strain relationships with a strain energy function. And a strain energy function is a description of the amount of work, the amount of energy of a piece of material that is done over a series of forces. And so this can give us insight into the structure-function relationship of tissue. Y.C. Feng, who many of you know, was the first to characterize the strain energy of tissues in general with this general formula, and it relates the amount of work done to material parameters, and again, these are material constants, of alpha, beta, gamma, and kappa, in relation to the amount of strain seen in any one direction, and this is as epsilon. And so we can see, we can take a material, its stress-strain curve, and fit this strain energy function and be able to define a certain material parameter as such for. And if we take this material and we expose it to a different environment and cause it to change its mechanical behavior, we can thus characterize that change as a change in the material parameter. And in this way, we can begin to correlate this mathematical relationship with the changes in structure we see. And so what Y.C. Feng also showed was that in particular to arterial mechanics, that the stress-strain curve of the artery he noticed that at low strains, the slope of the curve was proportional to the elastin modulus. And at high strains, the slope of the curve was proportional to the collagen modulus. And so again, we can see that when describing the mechanics, we can relate this to the changes in the structure that we see, especially from healthy to diseased.
So, sorry, just a second. You go back to the two slides. So,
Nobody saw that.
that was awesome. Actually, go back one more. So, which are the elastin and collagen moduli in this?
So this does not have a description of elastin and collagen. Further strain energy functions developed by other people have.
I want to see the Robert Shannon stuff.
So what? As Dr. Shandis would say, so what? What is the point of all this? Well, this becomes really important when understanding the mechanics of materials as it changes, and most especially tissue, as it changes from healthy to disease. And yes, please take a picture. And how it relates to the changes in the structure we see in the material. And this is important when developing therapies to attenuate the disease or reverse the disease, as well as it's important when we're actually doing tissue engineering design, when we're trying to design a synthetic piece of material that is supposed to emulate the tissue. And so I have to sum up Shauna Burkett's work, where she has a hypoxic animal rat model in which she had 3 cohorts. She had a 3-week normoxic rat cohort, and so these rats were kept at Denver atmospheric pressure, and that's about 120 millimeters of mercury pressure of oxygen, and then a 3-week hypoxic rat cohort in which rats were exposed or were housed in a hypobaric chamber emulating 18,000 feet above sea level. That's about a partial pressure of oxygen of 80 millimeters of mercury. And then another cohort in which there was a 3-week hypoxic rat model, and then these rats were allowed to return. They were brought back down to Denver atmospheric pressure and allowed to recover for 6 weeks. And so what she found, slightly hard to see here, is that hypoxic pulmonary hypertension does indeed recover. We can see that in the characterization of the mean pulmonary arterial pressure, in that it significantly increases from control to hypoxic to values above the standard definition of pH, and upon recovery, they reform back to the normal healthy values. What she also showed was that the compliance, and compliance is the inverse of stiffness, that the compliance, and she showed passive and active. The difference between passive and active is passive, not engaging smooth muscle contraction, and active engaging smooth muscle contraction. What she showed was that the compliance was severely decreased from the controls to hypoxic and did not seem to go back up in the recoveries. And she also noticed a slight correlation with pulse pressure. Pulse pressure is the difference between systolic and diastolic pressures in the pulmonary artery. She saw that it went up significantly and decreased slightly. And so all of her work kind of helps pose the question that I'm trying to answer, and that is, what causes the vascular stiffening to remain during hypoxic recovery when supposedly pulmonary hypertension resolves due to the standard definition? And so the hypothesis is this: the vascular stiffening that's seen in hypoxic pulmonary hypertension does not resolve upon recovery, and we hypothesize this is due to increases in collagen and elastin content alone. So can we explain the changes in the structure that still remain for the amount of stiffening we see to remain? And so my specific aims are this. Aim 1 is to evaluate the wall stress in the pulmonary artery in each cohort that's control, hypoxic, and hypoxic recovery, utilizing pressure dynamic measurements. My aim 2 is to determine the relative amounts of collagen and elastin through histology. And aim 3 is to determine the mathematical relationship between the material constants calculated in Funk's equation, stiffness, and the amount of collagen and elastin of the PA in each of the cohorts. So aim 1 I'm going to talk about first, and that was to evaluate the wall stress. And again, I utilized the very same model as Shauna, in which I had control, 3-week hypoxic, and a 3-week hypoxic with 6-week return control rats. And so we first noticed for the hemodynamics that mean pulmonary arterial pressure recovers. From control to hypoxic, we see a significant increase. And from hypoxic to return, we see a significant decrease. It's important to note that the mean of the hypoxic group sits just below 25. That is probably due to the mild version of the hypoxic rat model. And so cardiac output returns somewhat. We can see again the controls significantly decrease with hypoxia and see a slight increase back in the recovery cohort. And just looking at the pulse pressures, we see control significantly increased from, control to hypoxia. There's a wide variation in the hypoxic group. And then returns, we see a regression back to control values. And all of this kind of sums up and verifies what Sean Brigette has shown, in that hypoxic pulmonary hypertension does indeed recover in the hypoxic rat model.
What happens to your PVR?
It's a good question. Do we have PVR?
We're working on that too.
Wait, if you go back 2 slides, cardiac output and impact
Yeah,
MPAP.
kind of recovers as well.
but not all the way, right?
Do you have been able to look at cardiac function? Been able to look at,
In relation to the amount of their body weight.
well, for example, ventricular contractility is altered, recovered.
Arterial elastance is altered.
Oh yeah, for sure. I mean that's the
Right.
actual. But do you have contractility?
Yeah.
I don't have them up here, but I can let you know after. And so, again, we can get pressure diameter measurements using a myograph. And this was developed by Blair in his lab. And so how this works is we have our piece of pulmonary artery, and we have it sitting in a tissue bath, or a water bath, in which it's sitting in physiological solution and at 37 degrees C. And we cannulate it on both sides, and we tie it down, and the physiological solution is pumped continuously throughout this system, and we have pressure transducers on either side that measure the pressure. And we can control the pressure. And so what we did was we controlled the pressure at 5 millimeter mercury increments from 5 to 55. And we measured subsequent diameters. And so in this sense, we can get a range of the change in diameters over a certain pressure range. And this is our raw pressure diameter data. On the left here, we have controls. In the middle, we have hypoxics. And on the right, we have the recovery cohort. And these are on the same scales. And initially, we can see that the control cohort has a wide variation in a wide spread of the amount of diameters that were exhibited, as compared to the hypoxic, and the returns do not have a significant wide range of diameters. And it's important to note that the slope of this is equivalent to the stiffness, and these were all held at the same pressures. And so to look at the wall stress, we can take this data and we can model it as an engineering type problem, as a geometric type problem. And we can take this cross-sectional area here and we can define the wall stresses directionally. The circumferential wall stress is the stress that is along the circumference of the wall. The radial stress is perpendicular transverse into the arterial wall. And the longitudinal stress is along the length of the artery. And so we can take these and we can actually develop calculations for these based on just the pressure and diameter measurements. On the left here, we have a thin-walled approximation. And so what thin-walled is if your radius to thickness ratio is less than 10. And when that happens, we can greatly simplify the calculation for wall stress to be just the internal pressure times its radius divided by thickness. For our pulmonary arteries, our arteries have a radius to thickness ratio greater than 10. And so we must utilize the more complex circumferential and radial stress equations. And we can see from here that, again, it is just a relationship of the pressures times the inner and outer radius of the lumen. And so once we can get the characterization of the wall stress with pressure and diameter, we can then convert it into the intrinsic domain and be able to relate it to the elastic modulus again, Poisson's ratio, which is also a material property of the axial to longitudinal stretch. And we can relate these to the intrinsic domain. And so I also wanted to say that we are not able to measure the thickness with our pressure diameter measurements. And so the way I estimated the thickness of the artery was utilizing the concept of isovolumetric deformation, in that the thickness is the difference between the outer and inner diameter in relation to the inner diameter equaling the area of the small lumen, and the area of the small lumen is equivalent to the outer diameter minus the total tissue area taken with histology. And so we can see that as vessel diameter increases due to pressure, our thickness decreases as well. And so here are, again, this is our pressure diameter data. And we take this and we convert it into the wall stress data. We can see here, again, these are on the same scales, controls, hypoxics, and returns.
Sorry, could you talk a little more about this? Is this just one sample rat, or this looks like
This is the entire cohort.
the entire cohort?
Okay.
And this is data for when you're increasing pressure and then decreasing pressure, right? All combined
Yes.
on one.
Yes, exactly right. Increasing and decreasing pressure, and this is all combined on the same plot. And so we can see initially, and also I want to point out that the recovery cohort has never been looked at before, so this is novel data. And we can see that the control cohort has a maximum wall stress at about 600 kPa, and the hypoxics and the recoveries have a maximum wall stress of about 100 and 120 kPa. We can also notice by looking at this that the amount of strains here are half that of the controls. And so we can further analyze the trends of these curves using Y.C. Fong's concept of breaking it down into an elastin-dominated region and a collagen-dominated region.
Can you go back one slide real quick? You show lambda z equals 0.01 millimeters per
Yes.
millimeter. What is the longitudinal stretch? Did you test multiple longitudinal stretches?
No.
Okay.
Nope, so we really didn't measure longitudinal stretch. We didn't stretch the material at all longitudinally, and we set it just at lax length. And so the amount of strain is very minimal in longitudinal direction.
Did you measure the longitudinal stretch?
We did not.
Because it's cannulated, and so it's tied off on both ends.
Sure. Okay. I'm just thinking the work that Blair and I did together, primarily Blair. He looked at multiple longitudinal stretches, and that helps with
Right.
the development of the strain energy function.
Oh, okay.
And so, as I said, we can break these curves down into an elastin-dominated region and a collagen-dominated region. I also want to point out that although we didn't estimate residual stress using the geometrical way, measuring the cut of the pulmonary artery, I estimated it from the intercept here. So at zero strain, we can estimate the zero stress. And also, I want to point out that we can actually estimate the intercept of the collagen-dominated slope as the point at which collagen fibers are engaged in the mechanics. And also for stiffness, again, the equation is the cross-sectional area times the respective modulus divided by the length. And so we also assume that this is the relationship of the modulus for collagen elastin is in parallel rather than series. This has been proven in literature as well. And so the method for which I was estimating the slopes was through a linear regression in MATLAB of the last 8 data points. And here it is. We can see in the controls, this is a best fit line for the controls with the collagen-dominated slope and the elastin-dominated slope. And here we have the same curve overlaid on hypoxics and recoveries. And initially, we can see that it does seem to line up well at the bottom of the slope. And so when we take a closer look at this, we can see that the line somewhat aligns with the hypoxic and returns, but most importantly that the slope of the elastin-dominated regional line seems to line up fairly well with the hypoxic and returns. And down here I have the estimated slopes for the collagen-dominated region and the elastin-dominated region for the control cohort. And so I did the same process for the hypoxics and returns, in which this is the best fit line for the hypoxics with the collagen-dominated line and the elastin-dominated line overlaid on the controls and the returns. And here we can see again that the elastin line seems to line up well with both the controls and returns. And again, if we look at the returns best fit line, it actually lines up fairly well with the hypoxics, indicating that these are very similar in their mechanics with the elastin-dominated region lines as well. And so we can look at this, the data overlaid, and we see that the hypoxics and the returns are very significantly different than the controls. And we can look at their best fit lines by themselves, the data points, and see that, yeah, the elastin-dominated regional slope seems to be very similar, but perhaps maybe not the collagen regional slope. And so when we fit the lines, we see, yes, the elastin slope seems very similar, but the collagen lines slightly different.
You have, okay.
Yes,
That's
so
what I was
yes.
looking
And so when we actually look at rat by rat, we see that the elastin regional slopes are not significantly different when compared from control, hypoxic, and returns. And so we see high variance here as well. But when we look at the collagen regional slopes, they increase slightly but significantly from the controls to hypoxics and even higher in the returns. And so this is actually really interesting to see in that we see, just a slight increase from 440 to 580 kilopascal on a slope. And if we think about this in a physiological sense, this kind of makes sense in that we see, we know literature tells us that there's an accumulation of collagen in pulmonary hypertension. There's also studies out there that show that there's perhaps differing amounts of different collagen types. So you may have a more increase of collagen 2 or collagen 3 present in the disease. And we also know that mechanical testing of different collagen types tells us that their range of moduli for collagen types in general range from about 0.1 megapascals to 10 megapascals. And so because we have such a wide range for different collagen types, we can maybe kind of see that this may be the reason why we see such a significant difference.
Do you happen to look at the moduli at blood pressures for each?
I didn't look at that specifically, so I don't know if we can take the moduli at one specific pressure.
Okay.
No, I didn't look at that. This is over the entire range of 5 to 55 millimeters.
So these are your early strain and late strain fits.
Yes, exactly. Early strain and late strain fits. Correct.
Yeah, I agree with Blair that it'd be interesting to see their operating moduli, but this is
And so when we look at the residual stresses due to the intercepts of the y-axis, we see that there is a significant decrease from control to hypoxic, and in returns, this makes sense because our wall stress is significantly decreased from the controls and returns. But these values are very variant, so we didn't have significance, and also it's 5 rats. But we do see a trend to decrease. Looking at the collagen fiber engagement strain, now this is again the point of the x-axis on the strain at which the collagen slope intersected. And so we can see that there is obviously a significant difference from control to hypoxic returns. And this makes sense in that if we think about this physiologically again, at low strains, our collagen fibers in a normal healthy pulmonary artery aren't really being engaged in the physiological pressures. But when we have a diseased rat, we have our collagen fibers beginning to be engaged at lower and lower strains. So, of course, the stiffness is going to increase because it's being dominated by the collagen modulus, which is much higher than the elastin modulus. And so when we look at the stiffness, and again, I calculated this with the cross-sectional area times the modulus divided by the length, and at low strain, so this is the elastin-dominated low strain region, we see there is an increase in the stiffness, but again, not significant enough. And that kind of makes sense in that we didn't really see changes in the slope of the elastin-dominated region. When we look at the high strains, we see that there is significant difference from the control to the hypoxic returns, and this also makes sense in that we see a slight significant increase in the collagen modulus. And so we can further characterize these stress-strain relationships using strain energy functions. And these are Y.C. Fung's original strain energy functions, in which he related material parameters such as C, A1, A4, and A2 in relationship to the circumferential and radial strain C. And it's important to note that C has a parameter of 4 kilopascals, while A1, A2, and A4 are dimensionless. And so this was done using least squares. And least squares is a method in which we take the point of the model, subtracting the experimental points, squaring it and summing it and minimizing that summation. And this was done in math. And so here's the initial strain energy function fits. We can see again that the hypoxic returns seem to fit well. The controls fit well at high strains, but the fit that I have lags a little at low strains. And I did a fit for each rat. And so here we have control hypoxic returns with their material parameters estimated with standard deviations. And so for the controls, the main value that has a parameter of force, C, has a value of about 2.5, where hypoxics and returns seem to have values of 12.4 and 12.3. And their associated fits given in chi-squared values. Chi-squared isn't intuitive. The R-squared values are here, and so The control is about 0.95, the hypoxic at 0.86, and the return at 0.84. So a relatively good fit, above 84%. Again, we can see with the fits without the data points. So now I'm going to talk about my second aim, which, if you recall, is to histologically characterize the tissue. And so we did this with utilizing two chemical stains. The first is mouse and trichrome. So we have controls, hypoxic, and returns again. And so how we did this is we took each pulmonary artery, we fixed it in 10% paraformaldehyde, and then we sectioned it transversely and subsequently stained for each of the chemicals. And here we can see that the blue is in collagen, and so this was done to determine collagen content. Here, blue is collagen, and pink is intracellular actin. We again did this with Virchow van Giessen, and Virchow van Giessen stains with black, which is the elastin, and pink, which is connective tissue. And so how we quantified collagen elastin was through image processing, in which I took the raw images of the pulmonary artery, I binarized them, so I converted all of the tissue area into black and white, and I thresholded then using MATLAB for amount of elastin or amount of collagen. And so I took this area, so I quantified the amount of pixels, total amount of pixels in this, and I divided it by the total area of pixels, and that's what I'm referring to as percent collagen, percent elastin. And so we can see that percent collagen remains elevated. From controls to hypoxics, there is a significant increase, and there's no significant difference between controls and returns. This correlates well with what literature tells us, and that we do see a significant increase in the amount of collagen that's correlated with an increase in the thickening due to hypertrophy. When we look at the percent elastin decreasing during pulmonary hypertension, this is also a significant decrease from control to hypoxic to return, but this is not as intuitive because literature tells us that elastin really shouldn't change during pulmonary hypertension. And so the reason I believe this is so is because if the total amount of elastin isn't changing, that the increase in area itself is going to diminish the percentage number because we're taking total amount of pixels of elastin divided by total area. And so if total amount of pixels of elastin aren't changing from control to hypoxic, it's going to decrease with the increase in area. And so
I was about to ask about that. Why not normalize?
These are normalized.
Oh, they are?
Yes. And so that's why you have a decrease, because area increases significantly. So if the amount of pixels of elastin stay the same.
Actually, you're good.
Okay. Well, so
I need more coffee.
I looked at the actual
There you go.
total pixel amounts not normalized of the
We're
elastin.
good.
And I see that they're not significantly different. So this makes sense in that technically our amount of elastin, as literature has told us, should not really change. And so I also calculated wall thickness using image processing. And it's kind of hard to see here, but I have 6 points across the pulmonary artery in which I measured thickness. And then I took the average of these 6 points for each rack, and I estimated the average of the thickness for each PA. And so we can see that for the general full thickness of the pulmonary artery, hypertrophy is unresolved. We see a significant increase from control to hypoxic, and not a decrease at all, or significant decrease in the returns. And this also coincides with what literature tells us that we do. If we look at the histology just visibly, we can see that there is an increase in thickness.
You have to look at RPH from these animals when you did your necropsy or just total vessels per high field from the whole histology.
No, we were just taking these are all 10x images as well.
I think you looked at RV free wall versus LV weights in another cohort. Is that
We collected all the hearts, and
Okay.
that's something. Yeah,
Okay.
that's our future steps.
And so aim 3 then is to correlate all this data that I've previously described in aim 2 and aim 1 to see if there's some kind of relationship that we can see if the amount of structure is relating to the increase in stiffness and modulus that we see. And so the first one is C1, which again is one of the material parameters in the Weisskopf equation, strain energy function, in relationship to the elastin-dominated regional slope and the collagen-dominated regional slope. And we see that at low C values, these are the control cohorts, we have a slightly lower collagen modulus, and that's in red. And that it kind of thresholds out and maximizes out at a plateau for the C values at above 10. And these correlate to the returns in hypoxic cohort. For the elastin-dominated slope, we don't see a very significant trend here, and that's because we don't actually see any any changes, significant differences in the elastin slope. And so we can.
What are the significance of these fits? I see a chi-squared, but what is your p-values for? These are both linear models. So
yes.
What's the statistic?
So this was an exponential fit. You can see that here. And so chi-squared, it's not significant. And this is a linear fit, and that r squared is very low. It's 0.01.
So how can you really draw any conclusions?
We can't. So this is not really telling us that there's any significant relationship.
Not even with the
Well, it seems there we can see a trend. The fit, we probably need more data points. So we need more rats, more data points to smooth this line out. And so when we look at the change in the percent of collagen increasing with the collagen modulus, we see that there is a slight correlation, but note that we have kind of two subgroups here. We have a population, and these are controls at the low percentages of collagen, and at the high percentages of collagen, these are our returns and hypoxics kind of clustering. And so when we try to see a general trend, we really only get a fit between two clusters, as well as there is no general trend again for the elastin modulus. And so the fits for these lines are the actual percentage of collagen versus the slope actually is fairly well. It's about 0.7. So the R squared is about 0.7, and this R squared is not so. And so we see when C1 increases with the stiffness, and again the stiffness is calculated from the moduli, that for the elastin stiffness, we have for the collagen stiffness, we seem to have somewhat of a trend, a general increasing trend with the stiffness. And that's probably because the stiffness equation smooths out any differences between the slope, because we account for the change in the area as well as the length. And so we see a general trend, and that fit is about 0.5 for R squared. And this elastin stiffness seems to display a trend as well. And that is also probably due to the stiffness smoothing out the changes in the data. And so we wanted to see percent collagen again to see how it related with collagen stiffness. And we can see again two distinct clusters that are controls and our hypoxic system returns, in which we can't necessarily fit a line to two clusters of data points. And that there is a general increase as the percent collagen or elastin increases, we see an increase in the collagen and elastin stiffness. So the low and high strength stiffness. And I also wanted to see how C1 correlated with collagen engagement strain. And again, collagen engagement strain is the point at which collagen fibers are engaged. And so we see that as C1 increases, so low C1s are correlated with the control cohort, we see that the low C1s correlate to high strain intercepts, so collagen is being engaged at high strains. And that there's a slight general trend, again, not as smooth as we would like, we need more data points. And then at high C values, we have low strain intercepts. And again, this makes sense in that collagen is being engaged at lower strains in the hypoxic returns.
Well, what would determine collagen engagement strain? Isn't it the looking at the strain energy function? Isn't it in the exponential term that determines that, not the actual value?
So for the collagen intercept, I assumed it to be when I was estimating the slope of the high strain region, and I estimated the intercept at which it hits the x-axis. So when I fitted the line, it was the point at which it intersects the x-axis.
But the C1 is the
C1 is material constant.
is the dimensional parameter, the first dimensional
Yes.
parameter.
Mm-hmm.
Okay, let's talk about this. I think there's a better way to look at this using funnels.
Okay. Should I move forward?
Yeah.
Then we correlated the percent collagen with the collagen engagement strain again. And we see that we do, again, have clusters. And we see this for most of the data. and that as collagen increases, we get a decrease in the collagen engagement strain. And this is intuitive as well, it makes sense. And we also see a relationship between the percent elastin and the strain intercept as well for collagen.
Did you by chance compute p-values for these correlations?
So I did for the chi-squared values, but for the r-squared, I assumed any r-squared value above 70 was.
Yeah, I mean, it's hard to say. You know, r-squared value above 70, if you have a sample set of 40, then yeah, I would say that's probably significant. But these are pretty small sample sets, and so when you get r-squares in the 0.38 or 0.4, without a p-value, it's really kind of hard instead of such a small sample to even know if they are significant or not. I mean, the red one, it's hard to say if that's significant. It looks like it's just a couple points up there that are driving.
So I'll say what we can take away from this is that we do see some type of trend, maybe not significant, we need more data points, but we do start to see a general trend. So I will conclude with a summary of everything that I have showed, in that material parameters were estimated using the YC-Funk's original equation, strain energy function, and that we looked at the recovery cohort, which has never been looked at before in terms of wall stress. The amount of collagen seems to correlate to an increase in collagen and regional stiffness. We see that just based on the trend. C1 seems to correlate with an increase in the collagen-dominated regional stiffness, again, general trend. And we definitely know to be true that the strain at which collagen fibers are engaged decreases with the increase in collagen. Yes.
For Robin Shankar and say, so what? What does this mean? What's the clinical impact? What's the broader impact?
I was about to do the same thing.
So what does this mean? It definitely means that as far as understanding the way the pulmonary artery behaves in diseased and healthy, that hypoxic exposure, which is thought to be a hemodynamically reversible pulmonary hypertension, we still see stiffness in the artery. And we know that increased stiffness in the artery affects your right heart function. It causes the heart to work harder. So in fact, you're not healthy as far as how your heart is functioning in order to produce the same force for pumping blood against a stiffer artery. And so we can correlate that with changes in our structure. We see a general trend with the changes in our structure. And so we can say that this stiffness is increased due to vascular remodeling. That correlates, we can see a general trend to an increase in the amount of collagen broadly. And so there are several limitations from all the analyses that I've done, and that is we are utilizing a single layered versus 3-layered model, and that we are modeling the medial layer, when in fact the pulmonary artery is a very complex 3-layered structure. Also, a limitation in the image processing for protein quantification. So quantifying collagen elastin would probably be more precise if we actually did Western blotting techniques. And so fortunately, we were not able to do that. And then a lot of our data indicates that we need longer recovery time.
Can you expand on that a little more, the recovery time, and how much time do you think you need? So I think we both know what I'm getting at. So
right.
if you could talk about that.
Yeah. So, we see that we have a general trend in the recovery cohort to go back to normal values, in both in the hemodynamics and in the stiffness that we see in modules. So would probably be better if we looked at longer recovery periods, so past 9 weeks. It's important to say that we are one of the only animal models that have looked at the longer recovery times for the hypoxic rat model. And so possibly maybe 12, we've looked at 15, maybe 20, 24 weeks to see how much do these values continue to trend downward.
Well, I wanted you to talk more about how long you expect the collagen that developed during pH to stay there.
So what Vitaly is mentioning is that we have new collagen being laid down that is not necessarily going to stay. It may get metabolized again throughout time. And so as far as talking about half-life of collagen and things like that, we know that collagen, newly laid collagen, that will be degraded over time. So it would be interesting to see how collagen changes over a longer recovery period in relation to recovery. And so future work would also entail using Phil Cow et al.'s strain energy function. And he breaks it down even further by relating the material parameters to things like density of fibers, orientation of fibers, morphology of fibers. And it makes it much more complex and relative to the changes seen in fiber orientation and fiber change. And so again, possibly Western blotting to determine most especially the different types of collagen. So if we can use Western blotting to see the changes in collagen type 1 and collagen type 2 or 3, that would be wonderful, and elastic content as well. And again, analysis of collagen types each cohort. And then I also want to say that this work will be presented at ATS this year, and the abstract has been accepted. And I want to acknowledge all of my advisors. That includes Dr. Hunter, Dr. Walker, Dr. Kayfetz, Dr. Dodson, as well as a special thanks to Shauna Burgett, who has been very wonderful to work with, as well as Lori Walker for her help in all the lab materials and equipment, and Dr. Michael Yeager for his mentorship in my first year. As well as this project would not have been done without the financial support of Dr. Hunter. This makes some questions.
Yep. I was curious if you had any specific comparisons you wanted to draw to functional parameters from the work you had at the beginning to some of the putatively causal factors that you measured.
Right, so seeing.
And then the second part of that question is I noticed that some of the functional parameters were very, very tight in one group,
Yes.
but not in another.
Right.
Usually when I see very tight physiologic parameters in one group, it means it's very critical to regulate that in one condition.
So